All right, so today we're going to go over some of the details and the practical aspects of doing neural network training, because the concept's pretty straightforward. You got the sklearn, you do fit and predict, and you're done. Okay. However, with the neural networks, there's usually some things you need to look at. Okay. One of them is this idea of the learning rate, which, as I've described before, for whatever reason, when you use the LBFGS, when you use that LBFGS optimization algorithm, for whatever reason, you can't change the learning rate. So the only thing I can assume is that they do some sort of dynamic learning rate that is changed automatically. And that's one thing that's quite common, is that when you have the learning rate, the weights will change very quickly. Maybe I should pull up that lecture real quickly to show you what I'm talking about in terms of the learning rate. And that's in the update equation when you take the partial derivative of your error and you use that to update your error. So in this equation, we're taking our weight vector, our current weight vector, we're finding the gradient of the error with respect to each one of those weights, and we're multiplying that by this thing mu, the learning rate. And so if the learning rate is large, then the weights will change quite a lot. And if the learning rate is small, they'll change in small increments according to however strong the gradient is. Okay? But if you have, maybe you start in this, this part of the errors of the inputs of this space of your weights W0 and W1, if you have a large the gradient's pointing you downhill this way, but if you have a large mu, you could end up over here, or you could end up way off in the distance, depending on what mu is. So one of the common things is that mu stays large in the beginning when you're training, and then as you train, mu gets smaller and smaller and smaller, so that as you get closer to the minimum, you don't take big steps to make sure you don't miss the minimum. But in the beginning, you might have to travel a pretty good distance in the weight space to be able to get where you want to go. Okay, so that's all I can think, is that they have some sort of dynamically changing automatic system for choosing the learning rate. I don't know enough about the sklearn stuff to know exactly what they do, but to sort of illustrate this, I want to, let's see, this opens figure 2, so let me do this. I want to run with some different learning rates. Now, this is the case where I've manually done the equation for the gradient descent. It is technically gradient descent because I've taken the derivative and hard-coded it in there, but it's in a simple case where I have the one weight and the one bias. So, for example, I put mu to be a very, very small number here, okay? And you can see, it moves very slowly, and we can see there are changes here every time, and if we wait long enough, we can see that thing moving. Let me start it again with a different random weight. So here you can see I started with that random weight, and you can see the line's moving, but it's moving very slowly, okay? And obviously, we want things to converge as fast as possible. We don't want our computation time to be very large. So I think even if I hack off 2 orders of magnitude, let's see what happens. So now you can see, it gets in there pretty well. It got the slope pretty well, and now you can see it's starting to try and raise up the y-intercept to get it up there. Still, it's not as fast as you might want it to be, because it's still not getting there, all the way there. Let me see, let's take another order of magnitude off, let's see what happens. So now you can see that's just way too much. It's diverging. You might have seen let me run it again, you can see the blue lines jumping back and forth, and then it just goes crazy and it never actually converges. So you have to be careful. So So let's try 0.05. Let's try that one. So here you see it sort of oscillates about the answer, and then it gets in there and relatively quickly is moving in on the right answer. Okay, so that 0.005, that's probably okay. 0.006, that oscillates and it seems like it's not going to converge. It sort of goes off. So, I don't know, it's not done yet, but it looks like it's eventually going to, end off somewhere that's not good. Let's see if we do 0.004. There, sort of jumped around a little bit, but not very much, and has gotten relatively well settled in. Yeah, and so, 0.004, something like that is, good. But it depends, and it depends on the problem. So depending on what problem it is, how many nodes you have, the learning rate there's not just one learning rate that is the best for every problem. And this is actually one of the, somewhat legitimate criticisms of neural networks, is that us as the human designer have to pick, these things, and it affects the performance. Now, like I said, I don't know what sklearn has done with their LBFGS. They apparently have come up with a pretty good one that sets that automatically for us. Now, that's one piece. Then another thing I want to do is I want to go back to the version of this code that does the sklearn implementation. This guy right here. Run this guy, and so this is trying to solve the parabola problem. And right now I have with 5 hidden nodes. Okay, let me go ahead and I'll put this as 2 hidden nodes. So here's the 2 hidden nodes, and you'll notice that that doesn't look like the one that I posted in the lecture. The one I posted in the lecture looks like where is it? Looks like that one, okay? And I got different results. And if I run it again, I get different results. There, oh look, that one's pretty good. That's just like the one that looked like for the 5 hidden nodes. There's one that looks similar to the one that I posted. That one's different. I mean, you can still see in some of these cases, let me see if I can get one of those back, but you could see that there were the 2 sigmoids in there. Now that one, obviously, you can see the 2 sigmoids. And I picked that one because you can see the 2 sigmoids, what's going on. When it actually fits it well, let me see if I can get one like that one. You don't obviously see the sigmoids, but one must be on the left in that nice, curve down. The other must be on the right, okay? And so this gets us to another very big issue with neural networks, is that in some sense they're stochastic. That means random. That depending on the initial weights that you set for them, usually you randomly pick a weight and a bias because you don't have any prior knowledge, you don't know where to start, so you just pick them randomly, and depending on which random start point, I end up in a different local minimum in the error space, on that error surface. There's lots of these little saddle points and local minima and global minima, valleys, and I'm not always getting into the smallest valley. Obviously, when I get the really good, that one right there, that's probably pretty close to the global minimum in the error space. But that's the one right there is a local minimum, and we're getting stuck there. So it really depends on how we which random weights we choose. So we kind of need to look at, oftentimes you run your neural networks multiple times to see what happens. Okay? And in this case, it's really easy. I run multiple times, and I mean, I can always be checking against the training points. The points, these magenta points, those are my training points. And I can tell that that solution is better on the training set than that solution. So it's obvious that I should not pick this one, okay? But it's not necessarily obvious whether or not, this one's better, okay? Now, what the problem is we might want to test this on other data, on other things, things that are not in the training set, and we don't know how it's going to perform on things that are not the training set. In this case, we can see it's nice and smooth in between the data points. It's nice, it's a nice smooth curve. So we can look at this data and say that is a good solution because I can see it interpolating nice between the points. Now, if you have your input space having 5 dimensions in your input space, you will not be able to know whether it does a good job in between data points. It's not going to be possible for you to know that. And so that makes it tricky. So to give an example, I'll put it on h equals 5. And you can see most of the times I get pretty good answers. But you also see here that there's little squiggles here. There's a little squiggle there, there's a little squiggle there. It's actually better in the training set if you compare this versus the 2-1. If the lines probably go closer to the exactly on the magenta points, but in between is worse than it was on the 2-1, generally. And we don't have any data in between those points. It's not being asked to evaluate itself in between those points. So if I'm only going on the training data, there's no way for me to know whether I have a good solution in other data that I haven't looked at yet. Okay? So in general, basically every time I run the 5, here's a good example. Every time I run with 5, I get good results in the training data. But this one is obviously, when we plot it, I know that that's not as good as the others, but that's because I'm looking at the interpolation between the points. And in general, you can't do that. You don't have that luxury of being able to visualize it and seeing that it interpolates well. And then we can make it even worse. Let's make this 20 nodes. Okay? And look at that. I mean, this little guy right there, obviously that's not good, but the neural network has no way to know that it's bad, because it's like going exactly through all the magenta points. And you can see here that when I run with 20 nodes, look at that. Okay, that's terrible. But it's perfect in terms of training. And we need to be able to have some way of helping us to determine what's going on here. And this is a classic case of what we call overfitting, where the algorithm, the neural network has tried so hard to get exactly the values of the training data that it has lost it, doesn't see the forest for the trees. That it's basically memorizing the training data and does horribly on everything else. And it's a very classic machine learning problem, especially with neural networks, because they're so powerful. They have if you give them many nodes, they have so much power to be able to, they can represent any arbitrary function with an arbitrarily small level of error. It's amazing, okay? But with power comes, the possibility to abuse it, okay? And here that power has been abused. Okay, so we need to be really careful about how we solve, how we go about and work on training these neural networks. So that brings me to another file that I have uploaded to D2L, so you can see that. And maybe I'll just go a little bit through this code to show you what's going on. I'm still going to solve a problem. I'll go ahead and run this just so you can see at least what the problem looks like. Okay, so this is again a polynomial. It's a third order polynomial that we're trying to fit. Okay, and so I'm going to do a polyval here with 4 terms. That's a third order polynomial. So it's this polynomial, typical third order polynomial that I'm trying to fit. Okay, and I'm going to add some noise to it. Okay, so I have the x, the lin space, and then I get the y, and then I'm going to add some random noise to it. And that's what you can see. The dots are scattered around the blue curve. The blue curve is the actual polynomial we're using, and then the dots are scattered around it to add some noise into the problem, which of course is very common. You almost always have issues where you got noise. And then I don't remember that polynomial. Did I actually use that one? I don't think I've actually used that. That's a fit. That's a polynomial fit to the noise, but actually I don't think I ever used that. It must have been something I had before. So then I take my x values, I reshape them into a 2D array with 1 column rather than being a 1D array. And then I go ahead and I'm going to train my neural network. Okay. I have 5 nodes in my hidden layer. Okay. I'll talk in a minute about what this max iterations means. You already know the logistic function as the activation function. I already know that. And this warm start, again, is something that I'll get to in a minute. Now, what I'm going to do is I'm going to use this really handy function called the test train split. And I've needed to import that from the sklearn model selection module. Okay? And what that does is it will take my input data, the X and the noise, and it will split it up into 75% of it allocated to one set and 25% of it allocated to another set. Now they call it train test split, and it depends on how you use this. I'm actually using it as a validation set. Okay, and that will remind you of the very first day, it's been a long time now, that we talked about training data, validation data, and testing data. Okay, and so the training data, obviously, it's used to update the weights in the neural network. You know, it's directly involved in the training. Then we often use a validation set, which is part of the training, but we use the validation set to help us decide whether we're doing a good job. Okay? Are we overfitting the data? It's sort of like a pretend test set. It's not really a test set because it's not unknown to us. We have it there, and we're using it to decide, are we overfitting or are we not overfitting, or have we run 20 times with different random weights, and which is the one that we should choose. We're using the validation set to help us make that decision. But it is not an independent set of data because we're making the decision on designing our neural network from them. And a lot of people will present, well, hey, look, I've got this results in the validation set. That's how well my network is going to perform when it's working. And that's not true. You're fooling yourself. You're lying to yourself about how good you're going to be if you look at the validation set, because it's skewed. You're making your decision on what your final network is based on that information. And then you have the test data, which truly is supposed to be independent of the training process. So you could, if you wanted to, use this test train split, and you would, this is sort of the old-fashioned way of doing this, is you would do the test train split, you'd save 25% of the data, you'd train with the 75% of the data, and you'd train and you'd find, well, what is the best network for the training data, and then you take that and you apply it to the test set and say, okay, all right, it wasn't as good. Maybe I got 90% right in the training data and I only got 80% right on the test data. Okay, it works about 80% right in the test data. All right, but then I'm like, but that's not good enough. I want it to be better. And then I go back and I change something about the neural network so that the training is different. And then I say, oh yeah, now I've got 85% in the test set. Okay, good. And then I say, in this independent test set, I now have 85%, classification. No, you don't. Because you use the results in the test set to go back and change something about the neural network, it is no longer truly test data anymore. It was involved in training. It was what helped you to decide what your final neural network is. And it's very common that process, that test data will be used to change the neural network parameters, and then you're still going to say I'm validating on a test data. Okay, and that's not the right way to do it. You're overstating how well it's going to work in reality. So that's why we're going to use a validation set, and then we might have test data as well. So even though it says test train split, it's just splitting data into whatever percentage you tell it you want. Okay? And so it's going to return 4 things. The first 2 things are the 75% features and labels. And then the second 2 things it returns is the 25% features and labels. No, it's the other way around. Hold on. That is features. Features, training feature, 75% features, 25% features, 75% labels, 25% labels. Okay? And they'll be in the same format. If it's a feature matrix, it'll still be a feature matrix with the same number of columns for each feature, but 75% of the number of rows. Okay? So it's just really handy. It randomly goes through there and picks out which ones, to put in your set. So it's a very handy function. You just don't have to write it for yourself. Okay. So I'm setting some things here that I'm going to have as lists. I'm going to have what the mean absolute value in a training set is, in the validation set, and how many epochs I have executed. And an epoch is one process of updating the weights in your neural network. I'm going to say how many times I want to run through this, and I'm going to say that my best mean absolute error is going to be infinity, which is kind of neat. You can set the value to infinity, so if it will always be larger than any number. It's kind of a nice trick. Say float infinity, and it'll be the largest number they can represent. Or I don't know, maybe it's even, I think they do write it as inf. But anyway, it's kind of neat. It's kind of like MATLAB-y. Now, what I'm doing here is, let's see, one of these other figures, this guy here. Okay, so what I'm going to do here is I'm not going to let the neural network run from start to end. Okay, I'm going to do it in pieces. I'm going to let it train some, and then pause and take a look at things. And I'm going to let it train a little bit more, pause and take a look, a little bit more, pause and take a look, a little bit more, pause and take a look. And that's what these things of the max iter and the warm start have to do with. Okay, so what the max iter says is that if I've run for 30 iterations, then I will not train longer than that, and I'll stop. Okay? What the warm start does is that when you do a fit command, it will not automatically set the weights to random values. Because when you run fit, it automatically sets the values to random numbers. Okay, so if I do a fit and then I do another fit, it's like it starts from scratch. Okay? And so if we want to train for a certain amount of period and then continue, we need to do this what's so-called warm start being true. By default, warm start is false. And so when I run fit, I don't want it to choose new random weight values. I wanted to keep it what they were before, so I can continue to training as I go along. Okay, so I'm going to have a loop through here to go for however many number of runs, which right now it's 200, and then I'm going to go ahead and fit. Okay, and so it's going to have a warm start. It's going to start with its, it's going to have some random values for the weights, but it's going to use whatever is currently in there. Okay, now it's going to take, there's a data member for the neural network, the number iter, of course ending with an underscore, because they all do, and I'm appending that onto my epochs so that every time I stop, I know how many epochs it has gone. Okay, then I'm going to go ahead and predict with my training data. Okay, and I'm going to then append to my mean absolute error. That's what MAE stands for. So I'm going to measure the mean absolute error. And so I'm going to take what I was supposed to get and what I actually have. Okay, I'm sorry, the other way. This is what I'm supposed to get, the Y-train, that's the labels. This is what it actually predicted. I take the absolute value of the difference and the average across all of the samples, and I append that onto the mean absolute error train. Now, that mean absolute error is different. That's not the error measurement that we use for the gradient descent. In the gradient descent, we use the sum squared error. Okay, so I mean, one of the things, we're squaring it to basically get rid of the sign. So rather than taking the absolute value, we're squaring it. That makes above and below be equivalently looked at, but we need to square it so that the derivative doesn't have that discontinuity that an absolute value has. So looking at the sum squared error or the mean squared error, where I take the average, I take this and I divide by little n, that will give me the average squared error. But you know me as I'm particular about units. If I look at the square of the error, if the error was originally measured in feet, then now the squared error is feet squared. How do I, if I'm looking for how close I am to being a measurement, what does feet squared mean to me? Okay, so sometimes they'll talk about root mean squared error. Well, they'll take the square root of that so that it brings you back into the units that you're used to, but that's kind of roundabout. Why don't we just go ahead and take the mean absolute error? So I see what is the absolute value, the average absolute value of the error. So oftentimes we look at it's easier for us to interpret what mean absolute error means rather than root mean squared error or mean squared error. Okay, so I'm calculating the mean absolute value in the training set, then I'm going to predict for the validation set, and I'm going to calculate the mean absolute error in the validation set and append that to my MAE val list. Then I'm going to go ahead and predict all of the values. Okay, so that's both training and validation values. Okay, and so let's see. Then what I do is I say if the most recent validation mean absolute value, mean absolute error, the -1 says the most recent one, the one at the end of the list, if that's better than my current best in the validation set, okay, then I'm going to say, okay, well, if this network does better on the validation set than any other network has previously, I'm going to make this one be my best one. Okay? So rather than evaluating, say, I'm going to pick the one that's best in the training set, I'm going to pick the one that's best in the validation set. Okay? That will be a better approximation for how well it will do on the test set rather than looking at the training data. This is trying to avoid overfitting. Okay? So I'm going to go ahead and update my best mean absolute error. I'm going to open up a figure. I'm going to plot the actual data. Okay, I'm going to put the predicted data, what the neural network gives, and then I'm going to go ahead and put the validation actual data with as cyan. Okay, so the cyan dots are going to be the wait a minute, why do I don't even, that's figure 5. Oh, right. Okay, yes, that's figure 5. So this is only going to write to figure 5 when I have gotten a best, when I've identified something that's better than before. Okay? So figure 5 is only going to have the stuff that's better than before. And then it's going to put a legend on there with these labels. That's an interesting thing. It's a difference from MATLAB. In MATLAB, you would put the legend and you would type in here what the labels are for each legend. But in Matplotlib, when you do your plot, you add, there's another input argument called label, and you can give it a string. And so then each one of the plots, I say what the label is, and then I go ahead and just call the legend function. It'll plot the legend with those labels in there. Okay, so if I have gotten the best one that I've ever gotten, I go ahead and plot in figure 3. Okay, once this has trained, even if whether or not it had the best one, I'm going to go ahead and plot in figure 3. I'm going to open it. I'm going to clear the figure. I'm going to plot all the actual data. I'm going to plot the predicted data. Then I'm going to plot the trained the training data. So this is a line. That's the curved line of the blue one. So that's a curved line, you know, the curve of the original stuff, okay? The perfect stuff without the noise. Then I'm going to put the prediction, a curve of the prediction, and that's the orange one, okay? Then I'm going to take the individual training data. They're going to be the magenta ones. So the magenta ones here are the training data, and then the cyan ones are the validation data. And go ahead and plot the legend, pause so that it actually updates, and then I'm going to go into figure 4. Where's figure 4? This is figure 4. And what's in figure 4 here is I'm going to plot how the mean absolute error in the training set has decreased over time as I'm training. Okay? And then I'm also going to plot how the validation mean absolute error has changed over time. Okay? So as it's training, we can watch and see how well it does in one set versus the other. So that's, you know, the error, and then this is going to show you what the results are, and then figure 5, wherever figure 5 is, that shows us. Well, it doesn't have a plot in it right now because I must have stopped it in the middle of it trying to plot in it. That one shows us the best possible one that we found according to the validation set. Okay, so I need to make enough space here so we can see all these wonderful figures. Okay, so let's run it again. All right, so you can see here as it's training, the errors are getting smaller. This is very typical that the validation error will be worse than the training error because it's explicitly using the training data to get better, okay? And over time, the training, they're both, the training error definitely is getting less. Here you can see the validation error got worse for a while, and then it got better, okay? And you can see this is showing the validation data for the cyan points, okay? And the orange curve is the best one we found with the validation data. Now you notice the current one that it's working on right now, is this orange curve. And you see the orange curve change. Ah, look, we just hit a point where the validation error was better than before, and it updated in the best one. Okay? And so you can see, it got worse for a little while, then it got better, and now, I don't know, it looks like we're still, maybe going down, but there is definitely a gap here between the training and the validation, which is totally normal and almost always the case. Okay? And, the results here, I mean, you can't hardly blame the neural network because remember, it's only being updated according to the magenta points. So it's trying as best as it can to go through the magenta points. And you can see here, look, there's 3 magenta points clustered up here and 1 down there. So of course it's going to come closer to those 3 so that the error is higher. And then you can see, well, there's a bunch of stuff that's sort of on the line or below the line, so it dips down here to get to them. And then here, there's a whole bunch clustered up there, so then it jumps back up there to go through the magenta points. I mean, it's doing a really good job of going through the magenta points. But unfortunately, because of the noise, it's not perfect, okay? And as it turns out, the validation error and the training error, were matching each other. Now, so I'm not going to change anything except run this again with new random weights. So I'm just going to run it again, and you'll see we should get different results. Okay, so still generally the same thing. Validation error is worse. They both seem to be coming down. Okay. But here, this is the current one, and we watch this one changes. Changes every iteration. It's just not changing very much right now, so we don't see much change. And it looks like down here must have been the the lowest error, and so it's sort of updated. Okay, and it's different. The results are different. We can run again. See what happens now when we run it again. Look at that. The validation error took a spike up, and then it started coming back down again. Okay, and yeah, look at, and the data is random every time too. So look here, there's a gap from here to here. There are no magenta points. So it was doing some weird things in the middle there because it wasn't being evaluated on that. Eventually it sort of overcame that, okay, and got down here. And this is a pretty decent job. This looks pretty good, for as well as it can do with what training data it has. Now you notice here, the error in the validation set seems to be climbing, even though the error in the training set is getting worse. So we would never expect we would want to use this network over that. Now you can see this one's slightly different. You see how it's really, it really changed a lot to be able to go exactly through those 2 points and then jump up here. You can see that's not the best one. The best one is less abrupt than that down there. Okay, so you can see it is working pretty well by judging it on the validation set that that's better than just training forever on the training data. Okay, now that is going to become especially pronounced, okay, if we do something like this. Let's go ahead and change the number of hidden nodes. Let's see. Let me make it over. Where's my, let's see, go in here. There, right now there's 5 hidden nodes. Let me go ahead and put 20. Okay, and so now we see similar stuff, similar type of behavior. And what I'm expecting to see is that it should be able to overfit even more, and we might see some crazy stuff. It has more power to be able to go through the magenta points, and obviously, what it has here is definitely worse than the best one in the validation set. And here you can see the validation set error is climbing and climbing, obviously climbing, while the training set's getting better and better in the training set. But we don't want that. Look at that. Now it's getting really terrible in the validation set. Look at that. Here it's trying to go through these two magenta points, and it does awful in the middle because there's no points in the middle. And the validation points are down here on the bottom, so these validation points are terrible. Okay? And so this is very common, where especially if you have many nodes where you're giving it a lot of power, that it will very much, you can see this orange curve is obviously overfitting the data. It's doing more than it should, and it's a good thing we were evaluating on the validation set, because we got pretty, this orange curve is pretty reasonable. Considering how much noise is in there, that's not bad, that orange curve. Okay? Now, the overfitting becomes even bigger problem if you have less data. So right now I've had my linspace do 100 data points. Let's have my linspace do only 50 data points, half the number of data points. And here you'll see the overfitting gets even worse. Should, at least. Eventually, with 20 neurons and only 50 data points, 75% of which are in the training set, it should be able to, fit quite well, which is not going to do a very good job. And you can see even the best one in the validation set is still not very good. Okay? I have too many nodes for the amount of data that I have. Look at this. The validation set is even worse than using random weights. Here's using random weights. Our error is way up here. Okay, so it's worse. We should have just not even trained it and just chosen the randomness in the beginning. Okay, because so that's something to be aware of. Now, if I leave there to be few points, but bring down the number of nodes. I don't know. Let's bring this down to 5 nodes again. Okay, we probably won't get as bad overfitting. Here you can see it's still taking a while for it to learn the training data very well. Isn't that interesting? Oh, there we go. So that's not bad on the validation data. And as we let it train, look at that. We're even actually better on the validation data than the training data. That's just sort of a quirk of where the data was picked. Okay. Here's not a bad result. With 5 neurons, I'm getting a pretty good result, even with a little bit of data. But had I not been smart about this and chosen 20 neurons, I would think I can't get a good result with these neural networks. It's just not doing a good job. And if this wasn't a nice third-order polynomial that you can plot and look at, you might have no idea why it's not working. It's very hard to visualize the actual problem, so it's really hard to be able to detect what's going on. Okay? So that's actually not bad. With only 50 data points, I've done pretty well. That's actually surprising. Now, of course, the more data you have, if we have 500 data points and I go to 20 nodes, it probably will be okay. Because there's so much data in there, I'm not going to necessarily overfit. So you can see that's pretty good. Both, what I had as my best one in my validation set is still, pretty good. I'm getting all pretty good results. So this again really emphasizes the fact that you need lots and lots of data in order for these things to work well. Because obviously if I only had like 6 points, my neural network probably wouldn't be very good no matter what. But a third order regression would be awesome. So neural networks are really only as good as the data. Okay, and then they're also only as good as the human choosing the parameters. If you're not smart and choose crazy parameters, you're going to get crazy results. Okay, so the main takeaway here is that we need to look at how many hidden nodes am I using? Okay, and what is the difference if I run it different number of times with different initial starting weights? Because that is going to give difference. So that's all I wanted to talk about this. So I want to go ahead and pull up the project description. We'll talk a little bit about how this relates to what I'm asking you to do in this problem. No, we're done with cone detection. Go away. Orientation detection. That's what we're in now. So what I'm asking you to produce are figures similar to what I've shown here, okay? At least for the training, so you can show, as time goes on through your training, how does your training and validation errors, alter over time. Now, this is actually when I actually trained it, so that's actually data from this project here, okay? And it's nice and smooth. It looks like, it looks pretty good, okay? So I want you to produce a figure like this and put it as an image file showing a typical training run, because you're actually going to run many times. Okay, you'll notice I didn't put I didn't put any labels on here for the amplitude, magnitudes of these values. I don't want to give away too much, as you're getting things. Now, how many epochs total did I run? I don't know. That's still a mystery. Maybe I ran 5. Maybe I ran 5,000. You'll explore some of that. Okay. Also, I'm not giving any indication for what my mean absolute error is here, okay, what the absolute values are. Now, you will notice one thing is that this is on a logarithmic scale. When I did it, and I did it in here, I didn't use plot, but I used plot semilog y. So what that does is it puts a logarithmic axis on the y-axis. Let me pull up figure 4 here. Okay, it's not so noticeable here, but basically what will happen is that if this first error here is what something, it's about 3. Okay, 3 times 10 to the 0. Okay, and you might have an error on the order of 3. And depending on your problem, in this problem the error doesn't drop all that low, but you might go from 3 down to 0.3. And then you might still be getting better. You might go from 0.3 to 0.29, and then from 0.9 to 0.28, and and it might go down. But because of the scale, because you're going from 3 down to 0.3, you don't see that maybe it's decreasing significantly, but you can't see because of the scaling. So what the logarithmic scaling does is it lets you see the data over many orders of magnitude. Okay, and so you may not be that familiar with logarithmic scaling, but for example, this tick right here might be 10, and this tick down here, it would be 1 then. Okay, so if that's 10, then this one's 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, and so you can see there's a larger distance from 10 to 9 than there is from from some of the others. Okay, and so that just basically compresses the orders of magnitude, so you can see changes in large magnitude and see changes in small magnitude. And it's very common as the error decreases from something very large and heads towards something very small to use a semi-log axis to be able to see that better. Okay. So I want you to create a figure like that, okay? I also want you to produce a figure like this one. And what we need to know is, what is the best number of hidden nodes for this problem? Okay? We don't know necessarily. And again, I left the number off there. Maybe that's 1,000 and this is 20, or maybe that's 1, 2, 3, 4. Who knows? Okay? But we want to explore that. We don't know in the beginning how many nodes is going to be a reasonable number of nodes. Now, as you do more with neural networks, at least you can get a ballpark idea, and you might know where to start. But I didn't know how this was going to turn out when I first started it, and I just had to try some things. So what I did is, at each one of these, so I guess it can't be 1, 2, 3, 4. At the most, these could only change by an integer, because you can only have an integer number of nodes. Okay? So for this number of nodes, I ran multiple number of times, okay, with different starting weights. Okay, and so each one of these circles is for the same number of nodes, but is the mean absolute error in degrees for each one of the final runs after I've used my validation set to choose which is the best one. Okay, so this is the final result. This is, if I ran the neural network with that run, that one right there would be the one I would use for testing it with. with no other information. Okay, then I run it again and I get this one. That one's better, it has better validation error. Then I run it again, it's better validation error, and so I get different validation errors for the same number of hidden nodes, just with different number of starting weights. And then the magenta star is the average of those. Okay, ideally, when I've written some papers, I've run 100 times with 100 different starting weights, to get a really good distribution of what it looks like. Here I think I use 10. The more the better. Obviously, you don't want 2. 5 is probably too few, because you can see, look at that. There's a huge difference in the error between that one and that. This is not a logarithmic scale, so that's basically twice the error, or more than twice the error from one run to the other. So it makes a big difference what the initial starting weights are, because I get stuck in these local minima. So that star right there, that to me says on average, maybe that's what I might expect for, somewhere around there in my test set, maybe even a little worse. Okay? Then I do the same thing, another 10 runs at this number of hidden nodes. I get that average. And that average, you can see, when I use a few number of nodes, it's obviously not enough. Okay, it comes down, it comes down. Once I get down to here, it's basically flat here. Okay, it does seem like as I get more hidden nodes, it's more clustered. All 10 of these are clustered around the same place, but I even got a better one there. It's almost like if you have fewer nodes, you have a chance of getting something good, but you also have some likelihood that it'll be crap. Look, that one's not very good at all. But that's the best one out of all of the runs. There's more than 100 different runs in there. That's the absolute best one down there. Okay? But if I want, so I'm taking a little risk here. It's a little risky choosing this hidden node. Hopefully it will do well, but here it's consistent. Okay? And so you can see then as I get a large number here, I skipped to a bunch of nodes and skipped even higher. You can see as I've gotten a large number of nodes, this average is definitely worse than those. And as I get more and more nodes, I have worse and worse average, and I'm starting to spread out more. So obviously there's a point of diminishing returns where I don't want to increase the number of nodes anymore. I want to use somewhere down around here. And so I think in the way I did it is I did all of this stuff and I could see what was a good number of nodes, and I picked which was the one that had the lowest error in the validation set. And that's that one right there, and that's the one that I used to go ahead and test with. Okay? Then once you've, from this information, selected what is your one winning network using the validation, okay, then you're going to go ahead and produce a figure of what the error looks like. Now, I'm not going to give you the test data until you submit your project, but you probably will want to produce this figure, say, with your validation data, or maybe all the data. Okay, and so this says, for the ground truth angle, is that thing actually turned 0 degrees or 90 degrees or whatever, and what is the error in the angle? And we can see, it looks kind of random. It doesn't seem like there's any preference for high errors in one place than another, and that's sort of what you're looking for. You don't want to see something systematic that I do really well on low angles and do crappy on large angles. It doesn't appear to be that way. Okay, and again, I'm sort of hiding, this is my results on the actual test data that I'm eventually going to test you on, but I didn't give you, what my actual error was. I think, let's see, what did I ask you to do? You have to have test performance that the mean absolute error is less than 5 degrees, and your worst case out of the 360 degrees is 15 degrees. And again, I went ahead and did it myself, and made my network, and then took the test data without having ever evaluated on the test data and saw what I got, and I set these thresholds higher than what I got. Is sort of how I came up with them. Okay, so you can see here I'm asking you for your performance in some of the training data to be 1.5 degrees on average and no more than 5 degrees error. So I was able to get this on some of the training data, and and it was obviously worse in the test data, and that's normal. that you're going to train and you're going to get. It's like, wow, this is great. I've got an average of 1.5 degrees. That's not bad at all. I'm pretty good. And then you go and try the test data and it's up to 5 degrees. That's normal. And a lot of people will say, I got 1.5 degrees average error, and that's what they'll say was their performance, and it's not really an accurate way of doing that. Okay, so it's 10:50. Get going. Next week, we got all the stuff for neural networks presented now. What we're going to do next week, we'll look at how to do the image rotations and the data augmentation and some of that stuff, and we'll get cranking.